Here in this video, we are trying to derive different cases of Doppler effect. Let us see what is the first case is. When a source and observer have a perpendicular motion towards the other, what is the apparent change in the frequency? What is the apparent frequency? That's the equation that I want to observe, right? So let's talk about a case A. Imagine a source is in the state of rest and consider an observer revolving around the source in a circular path like this. So at this point, say, observer has a velocity tangential to the path. At this point also the same. At this point is also the same. So at any point, observer is having a motion perpendicular to the source that is in the state of rest. That means no part or component of velocity of observer is having relative velocity with respect to source. That means no relative motion between source and observer. That means there is no Doppler effect. That means apparent frequency equal to the original frequency itself in this case. This is the same even when you reverse the case. What do you mean by reverse the case? Like, what I mean by reverse the case is, imagine observer is in the state of rest. A source is moving in a circular path. Even in that case also, there is no apparent change in the frequency. So n dash equal to n itself. That is case A. Let's talk about case B. When a source is in a circular motion away from the observer who is in stationary, right? Both just little away. So what is the meaning of that? Let us try to understand. When observer is in the state of rest, a source is attached to a string and it is having a circular motion like this. So at this point, velocity of a source is like this, so is perpendicular to observer. Like I said in the previous case, there is no apparent effect. But at this point, velocity of a source is completely away from the observer. So due to this position x, there is an apparent frequency. And here, of course, it is perpendicular. There is no apparent, no velocity. But here you see, the source is coming towards the observer. Here going away from the observer, so the frequency will be minimum, apparent frequency. It is approaching the observer, so apparent frequency will be maximum with respect to this observer. So what we can say, nx, or I can say n minimum, that's what we have started here, is equal to v by t plus vs into n. Denominator, it shall be plus because it's minimum. And maximum of this case is v by v minus vs into n. Like we have done in the other case, in the previous video, we'll get beats because these frequencies are different. Number of the beats per second is maximum frequency minus minimum frequency. This is maximum, this is minimum. So Vn is common, 1 by V minus Vs by minus 1 by V plus Vs. This can be further simplified. Denominator is V square minus Vs square, V plus Vs minus V plus Vs. This V and V will be cancelled, multiplied by Vn. So our equation is Vn into 2Vs, this Vs plus this Vs, by V square minus Vs square. But we can further say, as Doppler effect is valid only when the velocity of a source or observer is much less than the velocity of the sound, Vs square will be much smaller than the V square. So this Vs square can be ignored. So the number of the beats per second can be written as V n 2Vs by this V square only, ignoring that Vs square. This V can be cancelled. So beats generated per second in that case is 2Vs into n by V. Like that we can solve. We have done this in the other video, in the previous video also, in some other format. But anyway, the equation is same. That's the second case. Let's talk about the third case. What is the third case? Source having angular motion from the observer. What's the meaning of that? Let me try to explain. This is an observer in the state of rest. Source is not along the line, but approaching the observer with a certain angle theta. So it's very clear from this that we can resolve this V, velocity of a source, into components. This becomes Vs cos theta. This becomes Vs sin theta. This sine component is not having any relative motion with observer because that is perpendicular. So I can ignore that part and I need to write only this Vs part, Vs cos theta part. So n dash will be, this is approaching the observer. V by V minus Vs cos theta into n is the equation. If suppose the observer is going away, then in the place of minus I could be writing a plus. That is the case C we're talking about. We can also talk about case D. This is observer having angular motion, the same with a slightly different scenario. So let us consider the source in the state of rest, but observer is not approaching in the same line but with an angle VO. So similar to the earlier case, I can resolve this VO into components. This is VO cos theta. This is VO sin theta. This sin theta component is perpendicular to the observer, so no effect. So n dash will be V. This cos component is approaching the observer, which comes in the numerator, so it is plus VO cos theta by V into n. Once if you see the basic derivations of the Doppler effect that were made, you can actually get all this if you have not got it here, right? So you shall have basic Doppler effect equations in your understanding to know how I am writing these equations, right? This is how we can talk about Doppler effect. So if you see the 5-6 videos that I have made on Doppler effect, you will get a complete picture of Doppler effect. Further, you can comment on any of the doubts that you have on this, right? Thank you for watching.